Hi guys, and welcome to the last lesson in this section. And this is going to be an informational section where we are going to talk about exploring other data management options with Python. So you have many options for managing large amounts of data. In this lesson, we'll look at traditional client-server databases, newer databases known as NoSQL databases, and how cloud storage is changing approaches to data management. Finally, you consider some powerful data analysis tools that can be accessed from Python using third-party modules. So first, let's talk about client-server databases. The traditional SQL database is rather different from Sqlite in the way it is constructed. In these databases, you have a database server process accessed over a network by multiple clients. The Python DB API is designed so that you can work with these databases just as easily as you did with Sqlite. Only minor changes in the way you initialize the database connection are usually all that it is necessary. Occasionally, you'll see minor changes to the SQL syntax, and the parameter substitution symbol is sometimes different too. But in general, swapping from one SQL interface to another is a relatively painless experience. Several reasons exist for wanting to adopt a client-server database or to migrate to one from Sqlite. The first is capacity. Most client-server databases can scale up to much larger volumes of data than Sqlite. In addition, they can be configured to distribute their processing over several servers and disks, which greatly improves performance when multiple users are accessing the data concurrently. The second reason for migrating from Sqlite is that larger databases usually come with a much richer set of SQL commands and query types, as well as more data types. Many even support object-oriented techniques and have their own built-in programming languages that enable you to write stored procedures, effectively putting the API into the database itself. Usually, Usually a much richer set of database constraints can be used to tighten up data integrity far beyond the simple foreign key checks that Sqlite performs. The biggest downside of selecting a client-server database is the extra complexity of administrating the database. Usually, a dedicated administrator is needed to set up users, adjust their access privileges, tune the SQL query engine performance, and do backups, data extracts, and loads. Popular client-server databases include commercial offerings such as SQL Server from Microsoft, Oracle, and DB2, as well as open source projects such as MySQL, Postgres, and Firebird. And the next topic is NoSQL. And as data storage needs have expanded both in size and in variety, several projects have been exploring alternatives to SQL. Many of these projects are associated with what is called big data, which usually relates to the harvesting of large volumes of often unstructured data from places such as social media sites, or from sensors in factories or hospitals and so on. One of the features of this kind of data is that most of it is of little significance to the database user, but amongst the detritus are gems to be had that can influence sales strategy or alert you to imminent failure of components or processes so that action can be taken in advance. The nature, volumes, and need for rapid access of such data means that traditional SQL databases are not well suited to the task. The solution has been a variety of technologies that go under the collective term NoSQL. NoSQL does not mean that no SQL is used, but rather it stands for not only SQL. SQL may still be available for traditional queries on these new databases, but alternative query techniques are also used, especially for searching unstructured data. Some examples of NoSQL approaches with typical implementations are document, which is from MongoDB, key value from Dynamo, columnar from HBase, and graphs with Allegro. All of these diverge to some degree or other from the traditional relational model of multiple two-dimensional tables with cross-reference. To get the best from these systems, you need to consider which architecture best suits the nature of your data. Many solutions are open source, but commercial offerings exist too. Although NoSQL databases do provide the potential for faster and more flexible access to a wider variety of data, they generally sacrifice qualities like data integrity, transactional control, and usability. The products are all evolving rapidly, although at the time of this course, when it's produced, they require lower level programming skills to utilize the data compared to traditional SQL databases that could change quite quickly. Most of the popular databases offer Python modules that facilitate programming them from Python. And let's also talk about the cloud. Cloud computing has become popular in recent years with its promise of computing on demand. This potentially offers lower costs, more flexibility, and lower risks than traditional data center-based solutions. It brings its own set of concerns, of course, especially for sensitive data or where network reliability is an issue. The biggest use of cloud technologies in the database world has been in combination with the NoSQL solutions discussed in the previous section and other big data solutions such as Hadoop. Many cloud storage providers offer these technologies on a software as a service basis. This offers an attractive option for those just dipping a toe into big data or NoSQL world. And one note on cloud is that cloud services usually rely on the premise that the data can be physically moved without notifying the client, so long as the service is not interrupted. New data centers can be brought online and data transferred to these transparently. Unfortunately, many corporate clients insist on knowing where their data is being stored. There may be concerns about data protection regulations, or more likely the lack of such, in some countries, and these concerns are frequently written into project contracts in sectors such as defense, government, and finance. If your cloud provider cannot guarantee adherence to the contract terms, you may need to look elsewhere, or may even decide that cloud storage is not appropriate. The advantage of cloud computing for the application programmer is that the data is abstracted into a virtual database located at a single consistent network address. The physical location of the data may change over time, or the amount of storage available may grow or shrink, but to the programmer it doesn't matter. This does not mean that normal error handling can be ignored, but it does mean that the code can be largely decoupled from the physical design of the data storage. One of the biggest providers of cloud storage and database technology is the online retailer Amazon. It provides storage and an API Amazon Web Services or AWS, as well as a proprietary NoSQL database called SimpleDB, in addition to several other open source offerings. Other cloud suppliers are starting to offer similar products. Many providers offer small amounts of free storage and access as an incentive to try the product before committing to a significant investment. Amazon AWS has Python support available, including a comprehensive tutorial to both Python and the AWS interface. So check out the documentation if you want to look into it. And similar interfaces are available or will likely soon become available from the other providers. And the last topic in this lesson is that I want to touch upon is data analysis with RPy. Although client, server, SQL, NoSQL, and cloud computing all provide solutions for handling large data volumes or many users, you have other data management issues to consider. Often the processing of large volumes of data is more important than the storage or retrieval. If that processing involves a high degree of statistical exploration or manipulation, Python offers a basic statistics module, which was introduced to the standard library in version 3.4. If that is not enough, there is the R programming language. R is a specialized language designed for statistical number crunching and on a large scale. Like Python, it has accumulated a large library of add-in modules, and many statistical researchers use R as their platform of choice, publishing their research using R. The good news for Python programmer is that there is an interface from Python to R called RPy that opens up this processing power without having to become an expert in R. Knowing the basics of R, especially its data handling concept, it is pretty much essential, but much of your Python knowledge can be applied too. You can find RPy2 on the Python package index and install it via pip, via the pip command. Data management has many facets, and this lesson and section has provided how Python supports you from small volumes to large, from simple data persistence through to complex data analysis. Once you have control of your data, you are in much stronger position to create powerful, user-friendly applications, whether on the desktop or on the web. And that's the next two sections we are going to talk about. First, we are going to work on the desktop applications, and then we'll move over to web applications. So this is the end of this section, and let's summarize what we have done. So in this section, you learn how to store and retrieve data so that your application can pick up from where it left off, or so that you can work on multiple different projects. You saw how you could do this with flat files using indexed files, DBM, pickles, and shelves. We then looked at SQL and relational databases using Sqlite and concluded with a review of some alternative technologies. Flat files are good for storing small amounts of data for saving the program's state information when it shuts down. They are less useful where multiple queries have to be made, especially if querying on more than one key value. DBM files act like persistent dictionaries that can only store strings. Pickles turn binary objects into strings. Shelves combine DBM and pickle to act like persistent dictionaries, albeit limited to using strings for the keys. SQL is used to manage data in a relational database management system, RDBMS. Relational databases are conceptually made up of one or more two-dimensional tables, each representing one logical entity. Cross-references between tables act as a model for the relationships between entities. SQL provides commands to build and manage the tables in a database, as well as operations to create, delete, query, and update the data within those tables. Python provides the DB API, which is a standard protocol for accessing SQL-based databases. The DB API primarily consists of two objects, a connection and a cursor. The cursor is the primary object used for executing SQL commands and retrieving their results. Results are returned as a list of tuples. The Sqlite database interface is provided in Python standard library, and you can download a standalone interpreter, as we did with Windows. Sqlite, as the name suggests, is a lightweight version of Sqlite that stores the entire database in a single file and supports a lightweight subset of the SQL language. Sqlite can be used in small to medium-sized projects, and it is then relatively easy to migrate to a larger database if the project expands in scale. DB API libraries are available for most major databases and can be downloaded from third parties. By using the DB API, it is possible to build data abstraction layer that hides both the details of the database design and the SQL language from the application programmer, further facilitating the migration process if it becomes necessary. Several other database technologies exist, and this is an active area of development with several NoSQL projects vying for popular support. These databases tend to have quite specific areas of applicability, and no single solution suits all scenarios. Many are focused on the challenges of managing big data and are well suited to cloud-based solutions. So that's it for this lesson and this section, guys, and the next section is building desktop applications. I hope you enjoyed this section, and see you in the next section. Okay.